Okay, so good morning, everyone. Good morning. It's really a joy and an honor to be there. I've been teaching at this course, so I think that this is my 15th year, so it's a lot. And it's always a very nice moment for me. So just to introduce myself, I'm Stefano Tebaldini. I'm a professor at Politecnico di Milano. I can see three of my former students here, which is always very nice. And I've been involved with ESA and especially with biomass for nearly 20 years today. So this course is about SAR basics and SAR tomography theory. So I would just like to introduce you with this very part of the lecture. It would be very fun for me to start showing you results with spaceborne systems and especially with biomass today. As Klaus said, we are having a lot of surprises. We see that P-band is new, so we see that we are looking at the ionosphere in a totally different way. We are experiencing new RFIs. We see in desert things that are new, in ice things that are new, and of course we have a special eye on the forest. So it's super exciting. We are in the pioneer, heroic-like phase of the research, when every result is like an epiphany, and this is really great. But when I was a student, I was always very upset when I was presented with the big picture alone, because I wanted to know the details. I think that students, especially in science, need to understand the things from the inside. And this is not very easy, because I know that you have a different background. Maybe there are electronic engineers here or physicists for who like working with waves and complex numbers and differential equation is like everyday's matter. But maybe we have people from like optic or geology, geodesy, for which this is not granted. So the first part of my lecture today is SAR basics. It is intended to show you that what we do, okay, I'm not saying that is like everyday food for everyone, but it's not esoteric, it's not difficult, it's something that you can totally master. And in many cases, this is just about, it only takes to fix some concepts, some things that do not have to remain untold. If you have this, then you can proceed and you will have the background, or at least the starting point to proceed in your exploration with the solid basics. The last part of this lecture is SAR tomography theory. And I realized that this can be a bit disorienting, because SAR basics, okay, yeah, we start with the SAR, but then we do SAR tomography, which we are presenting as the most advanced technique that we are using now. So why the hell I do the basics and then I jump to the final end? Well, because tomography, at the end of the day, we see it's conceptually easy. It's just an extension of the basic theory from 2 dimensions to 3 dimensions. So it just flows naturally. And so this is how I structured this lecture, and I hope it's gonna be effective. I will stick around all day today, so you will be welcome to stop by and ask me for more details whenever you need it. So let's start from the beginning. So the first radar lecture. What is a radar? Radar stands for radio detection and ranging. It is a technology to detect a target simply by sending a pulse, like then the wave travels until the target. It is reflected back, so that based on the if I can sense this reflected wave, then I can know something about the target. We should mention it is an active instrument, so it doesn't need any external illumination source. We just say that it's based on measuring a time delay. it is interesting because at the frequencies we use, we can penetrate through clouds. So it's an instrument that we can use in any weather conditions. And importantly, especially for P-band, especially for systems like biomass, our waves do penetrate. So they penetrate into forest, into snow, into ice. So we are not just sensitive to the surface, we are also sensitive to what's inside. What is a SAR? What is a synthetic aperture radar? Well, basically, you just take a radar. So a radar with just a system that send the pulse and then receive. Just imagine that you mount this system on something that moves. So it's like this. So you play this game for a very long trajectory, and then the magic comes. Because if you take all the recorded data and you process them with some, let's say, fancy digital signal processing technique, which we will see at least in its principle, then you can form a high resolution image of the scene. And this is an example. This is an MVSAT image of northern Italy. And it's a high resolution. By high resolution, I mean a few meters. So this is amazing. And by this, synthetic aperture radars are now ubiquitous in remote sensing. They are used for land mapping, for change detection, for topographic mapping, to map deformation. This is one of the most important applications. But there is more to it. As we said, microwaves also penetrate into natural media, so like forest, snow, ice, sand. And this gives us sensitivity to the whole vertical structure of the things. Beautiful. This is the, let's say, the pro and cons of using a radar. You are sensitive to a lot of things. And this means that in a forest, for example, when you see a pixel within a SAR image acquired over a forest, you need to think that this pixel feels the effect of any target, of any object within this region of space, so that it is a mixture of the terrain, of bushes, of trunks, of the mid canopy, of the top canopy. Everything is, let's say, mixed, and the game at the end of SAR signal processing for the specific case of forestry, the game that we are going to try to convey this week for using tomography, using polarimetry, using polarimetric interferometry, and so on, is to understand how to single out the different components and how to relate them to geophysical quantities, primarily like for forestry, forest height or forest biomass. So we say that this first part will be about SAR and SAR tomography. And so what does SAR tomography do? Well, basically, it is based on repeating the same orbit many ways from different positions. And in this way, we can pass from a 1D representation, so where we know that each pixel contains like the sum of all the contribution distributed over height, to a 3D representation, because we are able to, let's say, to focus this signal on the ground, on the mid canopy, on the top of the canopy, and so on. That is to say that when we say tomography, it means that we no longer produce pixels, we become producer of voxels. So a tomography produces like a set of images, each of which is referred to a particular height. For example, we can provide the SAR image at the ground level plus 10 plus 10 meters, plus 20 meters, and so on. And of course, this is relevant because biomass will be the first mission ever with a specific phase dedicated to tomography, and the first mission to provide a global coverage, or a global tomographic coverage of the forest. And this is the first example. This is the first example that was produced at the end of last year to show you how tomography looks like. Here we have the Tumucumaque Mountains National Park in northern Brazil. What you have here is a biomass image, and you see that we try to convey this sense of three-dimensionality by putting here a vertical section. So the idea is that the color scale here is telling you something that is related to forest density at different height. So let's say that blue means empty space, whereas red means a denser forest structure. So this is what tomography does. What's it for? Besides being a fantastic tool for engineers and physicists, it also has some practical use. Here I'm showing you 3 vertical sections from a campaign. This is AfriSAR, collected by DLR and ONERA. And you see, so this bottom, this bottom line here is the ground, whereas the upper line is related to the forest canopy. And you can see how much information we have here. If you compare it with a LiDAR measurement, you see the match. This is the ground as sensed by a high-resolution airborne laser, and this is the canopy. So this is a sort of a validation, if you like, that we can extract those two quantities from a radar. And indeed, tomography was already demonstrated to be a fantastic tool to retrieve forest canopy height, or to retrieve the topography of the ground below the vegetation layer. It was a fantastic tool to classify the forest type based on different indicators. And importantly, we had this experiment years ago, which was very important for us. We saw that even in cases where the total intensity, so the total signal of a single SAR, so a 2D SAR product, didn't provide a very good correlation with forest biomass. This is here. We have here the intensity of the SAR image, and we try to correlate it with the total forest biomass as measured in situ at this site. You see that there was not much of a correlation here, which is always very bad, of course, when you're building a mission to measure primarily forest biomass. But we try to play the same game by using, instead of the total intensity, the intensity of images produced by tomography. So we tested the intensity at the ground level, we tested the intensity at mid-canopy, we tested the intensity close to the top of the canopy, and you see that the correlation changes a lot. In this case, we had this result that the intensity at about 30 meters in a tropical forest is very much correlated to forest biomass, and this is exactly what we needed, and this has contributed to improving a lot our understanding of how to extract forest biomass out of a radar mission. This one, I can skip it. Tomography is also very, very nice to use if you are interested in glaciers. This is the beautiful Mittelberger Ferner in the Austrian Alps. And this is how it looks like with SAR tomography. So you have in the bottom panel, you have again a vertical section that was produced by an L-band airborne system, which we flew over the glacier. And this was validated with a ground-penetrating radar, which is basically like a cart that you walk on the glacier surface with the antenna pointing down. This is probably the best and most accurate way to see what's inside the glacier. It is not the safest way because you need to walk on the ice surface and there are crevasses here. You see them. So this is an interesting way to look at the glacier. And it's also an interesting way to look at the snowpack because, for example, with SAR tomography, you can study the snow and identify internal layering. So we do not directly see the snow composition with tomography. You see something with polarimetry. But we can tell what the interfaces are. And this is a super useful information for those who are interested in snow assimilation processes. Now, this was to impress you and hopefully to draw you in and give you a motivation. Now, as I said, I want these things to be understood from the inside. So now we take a step back and we need to say, okay, can we pass from this fancy representation, from this fancy introduction of radar systems to actually understand how to do the things? The answer is, of course, yes, or I would not be here. In my opinion, what you need to know is some geometry, something about waves, what's happening at the window, okay, and a little bit of radar processing. So let's get started. Waves. You know the origin of waves, of electromagnetic waves? It's really easy to explain. So just imagine that I am holding an electrical charge in my hand here, and you are doing the same. So we all agree that there is a force in between that can be either an attraction or a repulsion. And this force depends on the distance. So if I change the position of my charge, let's say that I want to communicate you something. So I move my hand with the charge in my hand, and at this point you are able to sense this modulation of the force because I'm changing the distance, right? But Einstein said that nothing can travel faster than light, including the information that this force has been modulated. So this information that the force is changing is not instantaneous. So you don't get it at the very same moment where I start shaking my hand, but it needs time to propagate, okay? This is an electromagnetic wave. So it's a perturbation of a static field. So it is an effect of the universal speed limit. It is always triggered by charges that are moved in a non-uniform way. So just imagine to shake a charge and you are producing waves. This is exactly what happens with an antenna. So you plug an antenna, the antenna is shaken, and this produces waves. And the propagation velocity in this case is the speed of light, which is also the fastest thing that we know. Now some mathematics. The way we describe waves are as a signal, S, that changes in space and time, and we usually express it in this way. So S of t minus z over c, where t is time, z is space, and c is the velocity. What does it mean? Well, just imagine. We fix a point in space, like the first antenna, and we measure the signal in time. So we measure the wave in time, and we get a graph like this. So see that this wave starts at more or less here. It has 3 oscillations. Or we can measure the signal at this other point, so 50 meters away. In this case, we get the same signal. It is just delayed by the time it takes to the wave to travel for 50 meters. So we express it as s of t minus 50 meters over the velocity. And you see that it is the same graph, it's just shifted, right? It's just delayed. You can do the other way around. Just imagine that you fix time, so you take a photo, and in this case you have a representation of the wave as a function of space. Just imagine to take a snapshot. If you could visualize the field intensity, you would see something that changes over space now. And so let's see the typical case of a monochromatic wave. A monochromatic wave means that the basic waveform can be expressed as a sinusoid with a certain frequency, so f0. This is how it looks in time and space, where the color scale means, so red means high, so a positive crest, and blue means low, so it's a negative crest. And you can imagine it's something like this. Huh? It's important that you can visualize it. So if we take a particular position, let's say that we measure the signal at 35 meters, then we get a graph like this. And in this case, the period, so the time it passes in between any two crests, is the inverse of the frequency. Or if we fix a particular time and we take a snapshot of the wave over space, then we have again a similar graph. In this case, the spatial period, also known as the wavelength, is given by the ratio of the propagation velocity over f0. So when you speak about waves, you probably know it. The electromagnetic people tend to speak in terms of frequency, optical people in terms of wavelength, but it's exactly the same. And now some geometrical introduction to radars. I always like to pass through geometry, because believe me, radars can become really, really complicated. You start putting in polarization, angular diversity, bandwidth, waveforms with weird coding and so on. And it can really become disorienting. So I think that it's important that you stick to geometry, because with geometry is like a map here, right? So you always know where you are. And so how to explain a radar in sheer geometrical terms? Well, let's say that you produce a wave. So this is your radar. So you produce a wave. Let's say that this wave goes everywhere around. And so if you send the waveform S of t, which means that if you excite your antenna with the waveform S of t, then it will shake the electrons within the antenna and it will radiate a wave. Let's say that how does this wave look when it reaches point P1 and this way? So it's just delayed by the time it takes to travel for r meters away from the radar. Then let's assume now that at this point P1 there is a target. You know, the target is a military expression, but in this case we don't want to hurt any target, so they are nice targets. And let's say that there is a car. At this point, this car will be radiated by the wave, so it is illuminated by the wave, and it will act as a new source of waves. So it will produce new waves. Again, for today, let's just imagine that those waves are again circular, so they go everywhere. And let's say that I want to characterize the signal that I measure at point P2. At this point, it will be given by the signal produced by the car, so this S1, simply delayed by the time it takes to the wave to pass from the car to position P2. So if I put all the things together, I have that the total signal is given by the transmitted waveform delayed by the time it takes to travel from the radar to the car and from the car to P2. So if now I consider how much time it takes to return back to the radar, then I see that the delay is twice the distance over c. And this is exactly a way radar do to measure a distance. So it's radio detection and ranging. So basically you send the signal is reflected, so at a certain point you are invested by a new wave, so you detect that there is something. And by measuring the time it took from transmission to reception, you can tell the distance of the object. And this way, and this means that after a single radar experiment, you are able to localize an object in 1D, in one dimension. You already know its distance from the radar, so you can tell that the object is on the surface of a sphere with a radius r that you could measure. With this information, we can now understand synthetic aperture radars. Synthetic aperture radar, you just repeat the same experiment as you travel, as you move. It means that from the first position, so from the first pose you send, you can localize an object on a sphere centered on this position. Then from the second position, you repeat the same experiment. So you can localize on another sphere with a center in this position, and so on. At the end of the day, or at the end of your experiment, you have that the target is bound to lie on the intersection of all the spheres. And if you compute this intersection, which is what I try to convey with this picture over here, then you have that the intersection is a circle that is centered on your trajectory at the point where the target is closest to the radar. So let's say if I take this big microphone as the target, let's say that I do my radar experiment, so I travel. At the end of the day, I am gonna know that this microphone is somewhere on this circle. So I have a 2D localization because I know its distance from this position, and I also know that it is somewhere here. With SAR tomography, you repeat the same experiment on different lines, which means that you are computing this so that at the end of a tomographic experiment, the target is bound to belong to the intersection of all of these circles, and all of those circles just intersect in a single point. So that's why tomography can give you three-dimensional localization capabilities. And so geometry is great. I think that it is a very robust approach, but it doesn't tell the whole story because there are missing elements. The first one is resolution. So for now, geometry makes you believe that you can localize a point exactly. And this is not true. You have a resolution. And then the other point is, what if there are many targets? Because for now we are just reasoning with a single target, but the truth is that we don't want to localize a target. We want to form an image. So how is that? And for this I need to introduce you some radar signals. So what is a radar signal? As we said it already, we transmit a pulse. What does it mean that we transmit a pulse? Well, generally, radar pulses are of these forms. So we call it g of t times a sinusoid. G of t is a short pulse. So just imagine that that the signal goes up and down, like this. And this signal is multiplied by a sinusoid. And so at the end, it will look something like this. So the effect of the sinusoid is to add this very fast modulation, which can be slower or faster, depending on the carrier frequency. Again, think about something like this. This would be, so what you are hearing is the acoustic equivalent of a radar signal, because it is something that is zero, then you hear a strong sound, so the intensity of the signal goes up and down, and also this is traveling at acoustic frequencies, so if you can hear it, it is more or less in between 20 hertz and what was that, and a few kilohertz. Let me say that the carrier frequency or the wavelength is perhaps the most important parameter in the design, because actually it is the one parameter that will determine to which features of the target your radar is most sensitive. This is a great picture by Tuileton, given at the Dragon in 20 years ago. And for example, what are the scatterers that are sensed by a radar out of a tree? Let's say that this is an Austrian pine, as we can see. If you use an X-band system from above, then you are quite likely just sensitive to smaller leaves, because the wavelength is 3 centimeters at X-band, and so typically you are sensitive to objects that compare with your wavelength. So at X-band, let's say that you are sensitive to the top of the trees. At L-band, 27 centimeters approximately, you are sensitive to branches and to the rest of the tree. At P-band, you are sensitive to larger branches. And if you go even down with the frequency, so a wavelength of 3 meters, then you just don't see the tree, you only see like a vertical stick. So the wavelength is super important. And we say that on a mathematical ground, what happens is that you send the signal is delayed by twice the distance over c. So this is the signal that you transmit, this is the signal that you actually receive. You see that we are adding elements. In the previous slides, I was just drawing signals that were just going up and down. This time it is the same, but we are adding this modulation that is due to the carrier frequency. So this is what we have, and we end up with this expression. So we apply the delay to the pulse and also to the sinusoid, of course, so because the whole signal is shifted. Now, what we do, until last year we will go on Wikipedia to look for the formulas to write the cosine of a difference, so to expand the cosine of a difference in different terms. Now we can go on ChatGPT, which is even faster, so we can do it. And this is what we get. We get that we can write the received signal in this way. So we have a first term that is multiplied by a cosine, and the second term that is multiplied by a sine. So we can split it in, we can write it in this way. Now the part that is multiplied by a cosine is called the in-phase component. This is electrical jargon, so do not reflect on it, just take it. The first one is the in-phase component, I, and the part that is multiplied by the sine is called the quadrature component, Q. Whenever so if you are into using radar data or data from any electromagnetic sensor, you probably notice that you get I and Q data. So this is why. It means that that you are provided with the I signal and the Q signal. And this is all you need, because you see, you already know that the wave has been modulated with a carrier frequency f0, so you don't need it. What you need is actually the information about the delay, which you have embedded in quadrature and in phase signals, and also let's say you also want to look at their amplitudes, because the amplitude of the received signal is telling you something about the kind of target that can have triggered it. So, like if you are receiving an echo from a cat, this term A is likely to be very small, because the cat is not very reflective at P band. But if instead of a cat you are looking at a metallic building, then you would expect that this term A to be very large, because the reflected wave is very strong. So basically here what we want to get are the information about the amplitude and of the delay, because the amplitude is telling us how, more or less, how big the target is, not exactly, but let's say so today, and the delay is telling us at what distance it is from the radar. Now, in all receivers in this world, like including your smartphones, you have a receiver, so you have circuitries that do some magic, and from the received signal they give you the I and Q components, which are then digitalized. So this I and Q component, those two, is exactly what is recorded in any receiver. So they're exactly the data that are produced by a receiver. And now, so I don't know how many of you are maybe, so let's say so, who feels extremely confident with complex numbers? Raise your hand. 1, 2, 3, 4, 5, 6, okay, good. The others do not despair, because now I have a mini course on complex numbers, which are, so the end of the story is that they are not complex. They are called complex. I don't know why, probably because mathematicians like to say that they do very difficult things. But the funny story is that using complex number actually simplifies our life a lot. And this is the reason why everyone uses it. So once those I and Q components are digitalized, they are represented in a single complex signal. So the I signal is taken as the real part, and the Q signal is taken as the imaginary part. Every paper, every book about waves, I would say at least since the 70s, uses complex representation. And why? So it's not that it gives you something more. There is nothing really intrinsically better in using complex number, except that all the trigonometric formulas becomes much easier, because they are converted now in the formulas of complex exponential. When you multiply two exponentials, you simply sum the argument. When you multiply two sinusoids, you don't. So it's much more difficult. So you need to remember a lot of, if you don't want to use complex numbers, then you will need to remember all the trigonometric formulas, and your equations will grow larger and larger and larger. With complex numbers, it's super easy. You just need to know that that when you multiply two exponentials, then you sum the arguments, and your formula will stay compact, which means they are more readable and more easy to interpret. So this is the reason. So this is our signal. There is also to say that a complex number can also be very efficiently imagined as a vector in a 2D space, and we all like vectors in 2D because they are easy to understand. And so in particular the I and Q parts represent the coordinates of this vector. The phase, so what is the phase? The phase of a complex number is just the angle that is formed with the real axis, and the magnitude is simply the length of this vector. Now I think that, okay, so going back to our received signal, this is what we get. So this I plus JQ can be written as A, so the strength of the wave, times the delayed pulse, times we have a trace, so we have a residual of the carrier frequencies that we use here. You see, we have an exponential whose argument is 2 pi f0d. And I forgot to mention, and I'm sorry, I'm just noticing now. So this, the argument of the exponential with the j is exactly the phase theta that we just defined. So, remembering that the delay is twice the distance over c, and that the wavelength is the ratio of the propagation velocity over the frequency, this is the model of the signal received by a radar. This is it. You see, it's very compact at the end. And you can identify all the relevant information here. We have the amplitude. This term is telling us more or less how big the target is, or let's say how reflective the target is. I made an example with a cat. So let's say that we have a cat and then a metallic cat. Of course, the metallic cat will be more reflective than the real cat, or the building will quite likely be more reflective than the cat. Then we have the delayed pulse. So we have the same pulse that we transmitted. It's just delayed by the time it takes to the wave to go from the radar to the target and then to go back. So, sorry, I got lost. We were saying that the signal is a very nice representation because you have the amplitude is here, the delay is here, and then you have the phase. The phase is 4 pi over the wavelength times the distance. So it is connected to the wavelength, so the kind of radar that you decided to use, and to the distance, which is the primary parameter measured by any radar. And this is where the magic starts. So all the magic of SAR is due to this phase here. And now, talking about magic, I need to go in the frequency domain. All the signals that we saw until now were represented by drawing their graph as a function of time, or by writing an expression like g of t, where t is time. If we do this, we say that we are representing the signals in the time domain, because we just imagine that a signal is something that at a certain point it goes up and then it does something and then it goes down. So it's a variation with respect to time. Please? Oh, thank you so much. Thank you. and you always learn something new. Amazing. For years I try. Great, thank you. So this is a time domain representation. But an alternative representation can be obtained by saying that the signal can be written as a collection, as a sum of different sinusoids. In this case, we have G1 times exponential of j to pi f1t plus G2 exponential of j to pi f2t, and so on. I could also write the signal in terms of real valued sinusoids, so like the sum of a bunch of cosines and sine, but for the same reason that I said before, at the end of the day, it's much easier to use complex sinusoids. A complex sinusoid is nothing else than a sinusoid where the real part is a cosine and the imaginary part a sine. So there is nothing more that you need to know. And good. Okay, so at this point it is correct to wonder, can we represent any signal as a collection of sinusoids? So is this true for any signal? Maybe there are signals that cannot be expressed in this way. Well, I don't want to convince you because there is someone much more important and good than me who already took this point and conveyed the meaning to students. So with the words of Professor Richard Feynman, in what circumstances can a curve be represented as a sum of a lot of cosines? Answer: in all ordinary circumstances. Except for certain cases, the mathematicians can dream up. Of course, the curve must have only a value at the given point, and it must not be a crazy curve which jumps an infinite number of times in an infinitesimal distance, or something like that. But aside from such restriction, any reasonable curve, one that the singer is going to be able to make by shaking her vocal cords, can always be compounded by adding cosine waves together. If Feynman said that, we can trust it. So we can trust that whatever signal we are interested in can be represented as a sum of complex, in this case, sinusoids. This is just a classical example. Let's say that this is my signal g of t, so something, a very short pulse, like woo, like this. This is if I represent it with just 3 sinusoids, not quite the same, with 13 sinusoids, 27, 37. When I put together 77 sinusoids, it's more or less the same, so we can buy this. So this means that in this way, we can represent a signal g not just as a function of time, but we can also draw or write the series of the amplitude of the sinusoids that it contains. So this is the graph of g as a function of time, and this is the graph of g as a function of frequencies. So this means that g is composed of different frequencies. If I want to know the amplitude of this particular frequency, I just have to see the amplitude of this curve. So time domain representation and frequency domain representation. There are 2 equivalent ways to express a signal, so to communicate to someone how the signal is. Now, with this frequency representation, I can finally introduce the concept of bandwidth. What is the bandwidth? Well, the bandwidth is simply pass me the term, is the duration of a signal in the frequency domain. So it is the interval of frequencies that the signal occupies. And for radar pulses, we can state this rule. Now you see that I'm a bit reluctant because it's easy to find counterexamples, but this would make this lecture too long and technical without any real need. So for today, just accept this, that for radar pulses, the signal bandwidth is inversely proportional to signal duration. So typically, a signal that is long in time has a narrow bandwidth, and the signal that is short in time has a large bandwidth. When I said before this is short in time, and so I said that this quite likely contains frequencies from like, let's say, 40 hertz to a few kilohertz. So for acoustic signal, a very large bandwidth, because it is a very short sound. My voice, which goes much slower, has for sure a narrower bandwidth. And then the final question is, how do we get to know which frequencies contribute to a signal? So imagine that you have a signal in time. How can you tell its frequency representation? Well, this is what the Fourier transform does. And how does it work? Well, this is the formula. This is the formula. Basically, just imagine that you have the graph of g of t. You have it at discrete times tn, so that you can read the signal at t1, t2, t3, t4, and so on. What you do, you focus on a certain frequency f. You multiply the signal by exponential of minus j 2 pi f tn, so by a sinusoid, by a complex sinusoid at the particular frequency f, and you sum. And this is the amplitude of the frequency domain representation of g at the particular frequency f. Okay, so still 5 minutes. Okay. Yeah, I think it's appropriate. So with this, we can now start to attach some physics to our geometrical interpretation of radars. And the first concept we need to attach is range resolution. What does it mean? We saw the signal that you receive from a single target. Let's say that we only have the blue car here, so the signal would be this one. So the amplitude due to the reflection of the blue car, the delay due to the distance of the blue car, and then the phase. But let's say that we have two cars now. Well, waves are... no, sorry, I was about to tell you that waves superimpose linearly, which is true. Then I thought that this is not always true. It depends on the features of the medium. When you have a lightning, this is not true, but we don't care. So this is just a complication. For whatever you will ever do with remote sensing, the signals are not so intense to trigger non-linearity. So we totally, you can reliably accept that if you have two targets, the signal that you receive is the sum of the individual signals from any of those two targets. So in this case, we have the signal from the first car and the signal from the second car. They are just summed. And how can we know that there are two cars? Well, let's say if I take a look at the magnitude of the received signal and I see something like this, so I see the two peaks. At this point, I can say, okay, there is a first target at distance r1 with some amplitude, and then there is another target at distance r2 with a bigger amplitude. So if I take a look at this graph, if this is what I receive, I know that at distance r1 there is something, and at distance R2 there is something larger, or at least something that can trigger a stronger wave. If I can draw this conclusion, it means that we are resolving the two targets. Resolving means that I am able to understand that there are two different objects. And I can do this. Why? Because I see two peaks. So two peaks and two targets. Now, if the distances of the two targets from the radar were too similar, then you would have that those two peaks would overlap. At this point, I do not longer see the two peaks. I see just a single peak. If I see a single peak, it means that I am not able to say that there are two things, so I am not able to resolve the two peaks. So for this, we say that the radar is able to resolve two objects because they have different distances, as long as we are in this condition. So we say that as long as the difference of the delays, so twice R2 minus R1 over C, is larger than the pulse duration. We say that the pulse duration is more or less the inverse of the bandwidth, and so we can draw this conclusion. So we can resolve two targets simply because they are at different distances from the radar, as long as the difference of the two distances is larger than this parameter that we call the range resolution of the system, and that is given by C over 2B. So we just characterize the radar based on its carrier frequency. We say that changing carrier frequency makes you sensitive to different features. And now we have the second parameter, the bandwidth. So the total interval of frequencies that your transmission occupies. This tells you your range resolution, so your capability to resolve different targets because they are at different distances, and so your capability to investigate reality. I think that, okay, just some example. Biomass has a bandwidth of 6 megahertz. This is because the bad guys of telecommunications did not allow us to use a larger bandwidth. So, okay, because of the stupid TV, we cannot use a larger bandwidth, but it's okay. So we have, with 6 megahertz, we have a range resolution of 25 meters. If we consider an L-band SAR, let's say that the bandwidth can range on the order of 40 megahertz to even 100 megahertz, so a resolution on the order of meters. If we go to airborne, to higher frequency SAR, like 10 gigahertz spaceborne SAR, like TerraSAR-X or Cosmo, the bandwidth can be much larger, and so the resolution can be on the order of a meter or even sub a meter. The best resolution I've had the chance to work with was with an automotive radar. So it had a carrier frequency of 77 gigahertz, so very high. It means a wavelength around 4 millimeters. And in this case, the bandwidth was some 4 gigahertz, which meant a range resolution of like around 5 centimeters. So you see that it changes very much. Of course, the argument is that trees are big. So for trees, 25 meters is enough. Now at this point, this brought me right to the concept of angular resolution. Until this point, we are aware of range resolution. This means one important thing. So imagine that I have a radar here, or that I am a radar, and I want to take a picture of you, a radar picture of you. So now we have range resolution. It means that what I can do is to send the signal, and then, let's say, if I focus on just this column, I will count as many peaks in my signal as many heads I see here. But the problem is that we do not have a one-dimensional scene. We have a two-dimensional, well, it's 3D actually, but let's say that it is mostly 2D. So the interesting part is in 2D. So I need to resolve you in distances, so in range, but I also need to resolve two different heads, so two different persons that are at the same distance from me, like you and you. You are at the same distance from me. So now you would produce a single peak. So to resolve you guys, I need an angular resolution. So I need to be able to resolve targets in range and in angles. And this is exactly what we do now. So we say that geometry provides you with this nice interpretation, so that the target has to stay on the intersection of all the spheres. So you have also a localization along your trajectory. But actually, the way it works with waves is more properly understood in terms of angular resolution. And we start by considering this experiment. So we have an array. It just means that we have a bunch of antennas. Just imagine that we operate each antenna at a time, so at its own time, so there is no simultaneous operation, so that we can collect the signal of the car at each antenna. We use here a monochromatic wave. It means that there is no bandwidth, or that, if you like, the signal is simply a single sinusoid. And so I can explain myself better. In this expression, we have the amplitude, we have the phase. There is no g of t here, because this is a simplified experiment, and so to make it simple, we forget about the g. And so we have that the signal that we received at the antenna number n has this form. It has an amplitude and the phase that depends on the distance of the car to that particular antenna. And then we go on. Let's try and put a Cartesian reference system so that I can now express this distance in the proper way. You see, it would be a function of the coordinate of the car, so with this x and y car, and of the coordinate of the antenna number n. And this distance, now this is a fundamental approximation everywhere in radar processing and everywhere in wave studies. What we do, you see, this distance has a square root. Square roots are difficult. We don't like them too much. So what we do, we linearize it. It means basically that we try to look for an expression by which we can express the variation of distance of the same car to the different antennas simply as a linear function. And this is a standard Taylor expansion, so it's super easy. And we have that this R car would be the distance of the car from the central element that I call here x0. So if I know this distance, and if I know the angle, this psi car, the angle under which the car is seen from the radar array, then I can compute the distances to all the other elements simply in this way. So I add the product between the sine of this angle and the difference between the position of antenna number n and antenna number 0. Don't think that actual radar processing is based on this approximation. Actually, we consider the square root and everything in when we do the real processing. But let's say that for your understanding and to accurately and intimately understand how you can get an angular resolution with a radar, this is more than enough. So it's true that it is an approximation, but don't feel that you are actually missing something. This is giving you 98% of the thing. In wave theory, we say that we are approximating the wave as a plane wave. Plane, it's just because we are linearizing this expression. And in this way, we have this. We say that under this approximation that we call the plane wave approximation, the received signal can be expressed in this way. So again, remember that we are forgetting about g of t here, just to make it easier. And so we have that the signal is given by a car, so the amplitude that lets me understand how big the car is, so how strong its reflection is, times this first phase. This first phase is just the distance of the car to the central element. And then I have this phase variation that depends on the position of your antenna. This term is equivalent to say that, so if you analyze the signal as a function of space, by which I mean as a function of the position of the antenna, x0, x1, x2, and so on, you see that you can write this signal as a complex sinusoid that is not a function of time. So don't imagine a sinusoid as a function of t. This is a sinusoid as a function of space, exactly as we saw at the beginning of this lecture. You remember the picture? It's better to take a look at it. This one, so we had the sinusoid as a function of space, so it's nothing weird, it is just a variation that goes with the space. And now back to where we were, here. We have now that if we take a look at the signal collected by the different antennas, we have a sinusoid as a function of space, whose frequency is connected to the angle under which the car is seen from the array. So what I want to say is basically that if we had a way to measure this frequency, then we would know the angular position of the target. And this is how it works. So let's say we map angular position, by nature, angular positions are mapped to frequencies, and in particular to spatial frequencies. So we want to measure this frequency, we need a Fourier transform. We say that the way we can understand which frequencies a signal is made of is to compute its Fourier transform. So this is exactly what we need to do now. And this is it. So this will be our signal. We compute the Fourier transform. We do it exactly as we saw half an hour ago. And this is what we get, or at least this is what we expect to get. This will be a single peak. You see, tack. The position of the peak, we call it f car, so the frequency of the car, and we know that this position is linked to the angular position, that this frequency is mapped to the angular position by this equation. So we are measuring, matter of fact, the angular position of the car. Actually, now, this slide's title is Angular Resolution. So where is resolution here? So we need to put resolution into the picture. And actually, let me tell you that this is not what we expect, what we actually find. What we actually find is something a bit more complicated. This is what we find. So we do not find a sharp peak. We find a peak with some bandwidth in this case, so with some that spreads a little bit across the frequency axis. It peaks at the right position, so if we take the maximum, this maximum corresponds to the actual spatial frequency of the car, but you see that it's spread across a certain interval of frequencies. And why? Well, we saw before that the duration in time of a signal is the inverse of its bandwidth, is the inverse of the width that it occupies in the frequency domain. So a short signal has a large bandwidth, a long signal has a short bandwidth. That was in time. And now we are in space. So what is the duration of the signal in space? Well, if we have an array of antennas for a total length of A meters, we can say that the duration of the signal is of A meters. So we are changing time to space, but nothing changes. It's exactly the same mathematics. So the signal has a duration of A meters. It means that in the frequency domain, it has a bandwidth, in this case it will be a spatial bandwidth, of 1 over A meters. As simple as that. And then we know that frequencies are mapped to angle in this way. And so it means that we have an angular resolution. Let's make the same example as before. This time I have two different targets. There is a car, there is a tree. The car is at an angle psi-car, the tree is at an angle psi-tree. The two signals overlap, so I have the sum of them. When I do my Fourier transform, what I get is two peaks. A peak for the car, a peak for the tree. If I take the maxima of the two peaks, I know the angular position of the car and of the tree. And now, why angular resolution? Well, we can resolve the two targets so that we can tell that there are actually two targets and not a single one, as long as the two peaks do not overlap. Exactly, notice please, I am repeating exactly the same reasoning that I follow for range resolution. So as long as we see two peaks and not a single one, we can know that there are two targets and not just one. So it means that the difference between the two spatial frequencies have to be larger than this spread, so it has to be larger than 1 over A. And if we account for the relationship between spatial frequencies and angles, we have that the difference between the two angles has to be larger than the ratio of the wavelength to twice the array aperture. This is in angle. This we call it the angular resolution of your radar. So we saw the carrier frequency, which states the sensitivity to different features. We saw the bandwidth, that states your capability to resolve targets based on the range, based on the distance. And now for a radar that has an array or a radar that is moved, it doesn't change anything, by a distance A, we can also talk of angular resolution. So the capability of the radar to discriminate different targets because they are in different angular position. So let's say that if I have to do a radar image of you guys, I could simply take a radar, move it along a linear trajectory, and I should calculate the length of this trajectory so that I have enough angular resolution to resolve you individually. This is exactly how it works. So now, okay, I anticipated the thing a little bit. Let's say that we want to have both range and angular resolution. What we do, of course, is to have a radar that transmits pulses with a certain bandwidth. So we put G of t back in, and we also have an array. And so let's just to repeat the concept. We have the first antenna, and this is the pulse we get. Second antenna, you see that we are a bit closer, so the delay is a bit shorter. Third antenna, this is the minimum delay. Fourth antenna, and fifth. So this would be the signal that you have after this experiment. And in this case, with 5 antennas, we have 5 signals that look like this. You see that the peak is not exactly at the same position. It follows this curve. This particular difference is called range migration. So this delay variation is called the range migration. It complicates processing a little bit. So this is a detail that we don't have to go through today, for which reason we will assume that we can neglect this range migration. So just imagine that the one thing that changes across the signals of the different antennas is the phase, because it depends on the position of the antennas. And this is exactly what you have. This will be the signal. So, say, if I simulate this experiment, this is what I get. So in this case, I have target number 1 and target number 2, target 3, number 4. If I run a Fourier transform with respect to the positions of the antennas, which in this case means vertically, then you see that I am forming peaks in a 2D space. Just imagine that every peak here is one of you. So if I played this game here, I will get as many peaks, as many students you are. And this is how you build a radar image. Now we pass from radars to SAR, finally. We saw the principle. I think this is the third time that I'm presenting these slides, and I will need to present it once more. So we say that the principle is that you fly, so the target is bound to belong to the intersection of all the spheres, and in this way you can localize it in 2D. Now, how do we connect this to the concept of angular resolution that we just saw? Well, the trick is to imagine that when you fly a radar, you are basically having the equivalent of an array of antennas. So that just imagine that you send a pulse. I can do this better. Let's say that you have a radar, and this radar is built such that it sends a pulse every second. So it's like, and now we move it. This is what you have. This is a synthetic aperture radar, nothing else. Why does the theory of antenna array help us understand how it works? Because it is actually the same. So basically, you can imagine that for every pulse I transmitted, you had an antenna, a component of this array, which becomes a virtual array, of course, at this point, because it doesn't physically exist. You are forming this array as you move. Or, jargon is that you are synthesizing this array as you move, and this is also the reason of the name. So we said that you send a pulse every second, so it's like this. So in this case, we say that the pulse repetition interval, the PRI of the system is 1 second. Of course, you are moving, which means that this is equivalent to have an antenna array with a spacing between any two antennas given by the PRI times the platform velocity. Now, the one problem with when you pass from antenna arrays to a synthetic aperture radar is to understand how long the equivalent array aperture actually is. So we saw that in our mental experiment, to gain angular resolution, I need an array of a certain length, say of A meters, because this gives me an angular resolution that is lambda over 2a. Now, take the case of a satellite. It flies continuously. So if it transmits for 10 minutes, it means that it keeps transmitting for like hundreds of kilometers or even thousands of kilometers. Does that mean that the equivalent array is 1,000 kilometers long? This is the question. It actually doesn't mean this. And why? Because you need to think that when you have a radar that emits pulses, it only transmits on a certain beam or on a certain cone. So actually, when I start my experiment here, just imagine that my clap is only heard by the people that are in this region, but you cannot hear it. This means that my energy, so the energy that I radiate only is only absorbed by you guys of the first two or three lines, and reflected back only by you. All the people to the left hand of this room are invisible at this point. You will be visible as I move, and so at this point you start to reflect my wave. This means basically that at this point the target is completely invisible. At this point we start to, so the target starts to respond, it keeps responding, and now it's gone. So in a synthetic aperture radar experiment, a biomass, sentinel, whatever you like, the target stays illuminated only from a fraction of the time. This is super important to get. And the length traveled by the platform in this fraction of time is called the synthetic aperture, A. This is the equivalent, this would be the length of the equivalent antenna array. And this is what you use to calculate your angular resolution, which now we can calculate it. Let's say that we have, so let's say that we have a particular antenna that radiates over a certain sector. This would lead to an angular resolution, and this leads to a synthetic aperture AS. So by the formula that we saw before, this leads to an angular resolution delta pcs equal to the ratio of the wavelength to twice the synthetic aperture. So it's exactly the same. Just imagine that you have an array of antennas here. Now if you multiply by the range, you have the linear resolution. So basically, you can imagine that if you have the capability to resolve people or targets because you have an angular resolution like this, so this can be like of some 10 degrees. Well, this can be enough to resolve you when you are close, but when you go farther away, then we have an increasing linear resolution. So basically, this delta x, which would become now your capability to resolve any two targets just because they are at different positions along this direction, is given by the angular resolution times the distance. And if you put in the equations that links the synthetic aperture to the length of your physical antenna, which I didn't comment on, so don't worry, just take it as an external data, then you end up with this formula. You end up with that for a synthetic aperture radar, the along track resolution, which again means your capability to resolve two targets because they are at different positions along the direction of flight, is approximately half the length of your antenna. And this is wonderful, see? It doesn't depend on the wavelength. So if you take a look at the satellite, you can more or less say what is the along track resolution that it will provide. We saw the example of biomass, a bandwidth of 6 megahertz, and we saw that the range resolution is C over 2b, so the range resolution is of 25 meters. It's not super brilliant, but it's okay for trees because they're big. Now, you probably heard about this reflector of biomass. Klaus just showed it in the first part of the lecture. So do you remember how big that is? You saw that biomass has this huge antenna reflector. Do you remember more or less how you, yeah, please? 15, it was 12 actually, but okay, yeah, more or less, yes. So it is a reflector with diameters of 12 meters. On this basis, what is the long track resolution of biomass? 6. Actually, it's around 8 because there are some signal processing technicalities in between, but you see that we are not far. And so again, if you take a look at, so now Google SAR satellite pictures or data based on the size of their antenna, you can tell that you can have an idea of the along track resolution. If you know their bandwidth, you have an idea of the range resolution, and so you have an immediate assessment of what kind of resolution those images can give you. So, not bad. Now, and this is the last time I show this slide, we have that. We started from the geometrical interpretation. We say that you carry a radar, so the target has to be on the intersection of all the spheres, which means that, so geometry tells us that at the end of a synthetic aperture radar experiment, the target has to belong to a circle that is centered on the trajectory at the position where the target is found. Again, for this mic, if the trajectory is like this, here is the circle. This is a geometrical interpretation. Now let's pass from geometry to physics. This is a physical interpretation. The target is resolved within a region of space that is now something, so it's no longer an ideal circle. Now it's something more like a bicycle tire, you see. The size of this bicycle tire is the range resolution in this direction and the along track resolution, delta x, in the other direction. So imagine that you have a sort of tire like this. This is the physics of your radar. Let's say together with the wavelength that states which element you are sensitive to, this is the physics of your radar, because it basically says that, and this should be the next slide, it basically says that when you look at the single pixel of a radar image, you need to imagine that whatever is found in this region, in this bicycle tire that passes through that pixel, everything in there is lumped, is summed. So you are sensitive to whatever stays in this region of space. This is called, and this is a super important concept, this is called the resolution cell. So the region of space that you can resolve. What does it mean? Well, let's imagine that this is a SAR image in the coordinate of range and azimuth. I am just realizing now that I didn't define azimuth. Azimuth is x, so it's the direction of flight, so super easy. And range is just the distance, so I can go back basically. So the azimuth here would represent this direction, and range is the minimum range. So it is the distance from the trajectory to the point orthogonal to the trajectory, this one. So we have a SAR image. For each pixel, we need to think that we only see the integral along this area. So for example, if in this pixel we have a car, so the blue pixel means that we have a car, it means that this pixel value is only determined by the reflection from the car. So as a first approximation, we can say that the complex value of this pixel is given by a car, so the parameter that is telling us something about the strength of the reflection, and the phase that depends again on the wavelength and on the distance of the car to the radar. We can have a different situation. Let's say that we have different trees in the same resolution cell, so they collapse in the same pixel. In this case, we have that the value of this pixel doesn't result from a single target, but it results from different targets. We say in jargon that it is the result of the interference of different targets. And so we have that the value of this pixel is given by this sum. Let's say that we have a certain number of targets, and so you have A1, like imagine like the first tree, A1 times exponential of minus j 4 pi over lambda r1, then plus A2 exponential blah blah blah. So it is the sum of many complex numbers that contribute to the same pixel. Why am I stressing this so much? Because again, this is something that you really need to understand, especially if you do optics, to have a fair idea of what a radar can give you. Now, the next slide. This is an image from an airborne experiment. It is a P-band airborne SAR flown by Onera in French in French Guyana. So here it is a tropical forest. The image is 4 by 9 kilometers. This is range, and this is azimuth. So we were flying in this direction. I think that was the near range, so the aircraft was flying like this. Near range and far range. What to say? So the resolution is 1 times 1 meter. So 1 meter in range. This means that the bandwidth was 150 megahertz here, and 1 meter in azimuth along track, from which you can tell the length of the synthetic aperture, which would depend on the antenna. There is a lot to say here. First, you see colors here. So why do you see colors? Well, we just say that or rather, how do we compose a SAR image? So first thing that is usually untold, a SAR image is a complex entity because each pixel has a complex value. It has an amplitude and it has a phase. You see it here. Amplitude, phase. But when you take a look at a SAR image, typically people only represent the magnitude. So this is just the amplitude of each pixel. We are not visualizing the phase here. Here, for this visualization, we are just throwing it away. Untold too, why the colors? Because those are actually 3 different SAR images that are color-coded. So there is one image coded in red, one image coded in green, one image coded in blue. So this is a color composite image, and those 3 images were obtained by changing the polarization. So this is an advanced course on radar polarimetry. It is the first time that I mention in polarization. I have a few slides later on, but for the time being, just imagine that, okay, we are doing 3 different experiments somehow at the same time. So we collect 3 data, we process them in the same way, and then I am showing here the magnitudes just color-coded. This is how this picture was done. Now, what I want to draw your attention on is on this. This is a close-up of the forest. I don't know if you see it on the screen, with the beamer. It's pretty clear here. You see that it looks noisy. So this is a forest. If you take a look at an image of the forest from an optical sensor, even if it's not super high resolution, you see a nice green. So it's like uniform. It's more or less like you would paint it. You take the green painting and you go like this. This is not the way you would paint it. You see, you have dark green and bright green, and it looks a bit like salt and pepper noise. So it's like you had different brushes, one with dark green, the other with bright green, and you are going like ta 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 ta. Huh? This is what it looks like. So it's quite different from an optical image. Why? Because of interference. We say that a SAR image is the wave penetrates. So the SAR pixel is sensitive to whatever stays in the resolution cell. I can finally say that. Now you know it. So whatever stays within the resolution cell, within the bicycle tire, contributes. And the formula is this one. The value of each pixel is given by the sum of many complex numbers with an amplitude and the phase. So, to understand this easily, let's assume that instead of many elements, we have just two. So we have the red target and the blue target, say that representing the ground and the upper canopy. So based on what we just studied, we have that the value of this pixel is given by the signal from the ground, and I am also assuming that I have the same amplitude there, just for sake of simplicity. So by the signal from the ground, which comes from a distance R1, within this resolution cell, plus the signal from the canopy, which comes from a distance R2 from the same resolution cell. So the resolution cell has a physical size, and so inside the target inside the resolution cell are at different distances, slightly different distances, yet different distances. And this is what we have. So if we visualize this sum using the analogy between complex numbers and vectors, remember that the complex number is also a vector in a 2D space, it means that we need to sum the red vector and the blue vector. I get that you all remember how to sum two vectors, right? Yeah, okay, we're fine. And so we have that we produce the black vector, which is actually the complex number of that one pixel. It is the result of all the target within the resolution cell for that pixel. And you see that the magnitude of this vector, so the length of this vector, depends on whether the two vectors, the blue and the red one, are aligned or not. When they are aligned, you see, we say that there is a constructive interference. And so the resulting magnitude goes up. We have the brush with a bright green. But when they are not aligned, the amplitude goes down. And so this is the brush with a dark green. Of course, within a forest, we have all kinds of situations. So we have all shades of green, if you like, and this is what creates this salt and pepper-like image. This phenomenon is called speckle. Macchioline for Italian students. So it's like ta 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 ta. Now, is that bad? Is that bad? No. I would say that it's bad if you are used to optical images, because you will look at the radar image and say, oh my God, it is super noisy. This is not noise. This is physics. If you are used to looking at a radar image, this is okay. I would say that this is even more, this is it. I would say that this is even more informative, because based on the brightness, based on the variation of brightness, I can say something about the variation of the distribution of the targets within the resolution cell. And by the way, this is what enables interferometry, but this is another story. So for me, it is okay. But let's say that if you are like disturbed by this phenomenon, what people do is to implement a speckle filter. What is a speckle filter? Well, it's a processing tool to pass from here to here. Again, it's not very clear with the beamer, but let's say that the image on the right looks more uniform. So we have reduced this speckle thing. How does it mean? Well, the term speckle filter looks like very sophisticated, and indeed there is a lot of literature with really sophisticated approaches. In its simpler implementation, what you do, you take a magnitude image, so an image like the one we just saw, like this one, and you do a moving window. So basically you substitute the value of each pixel with an average of the magnitude of its neighborhood. And this way you are reducing resolution, indeed, but you are making your image more uniform and more homogeneous. So you pass from a speckled image that is at high resolution to a less speckled image with a lowered resolution. How to choose this trade-off depends on your psychology. If you are a radar person, you are totally happy with this one, but if you like to see something more homogeneous, then you want to despeckle a little bit. And then, just one word on SAR polarimetry. Now, you will study SAR polarimetry in details, so later on in the course. So this is just to say, this is just to mention why Francesco this afternoon will show you colorful pictures. Well, one thing that I didn't mention about waves is that they are polarized. What does it mean? That when I transmit a wave, the vector field, so the vector that represents the electrical field, can have different orientation. And physics says that if a wave propagates in this way, so from me to you, the field is always orthogonal to the direction of propagation. So let's say that this is the vector field. The way it travels in this way, it's going to be something like this. And this I will call it a vertical polarization for an obvious reason. I can create a wave with a horizontal polarization, so in this case it would be something like this. So polarization is a super important property of waves. SAR sensors can transmit and receive both in horizontal and vertical polarization. So at the end of a SAR experiment, of a polarimetric SAR experiment, you have 4 data. You have HH, so you transmit horizontally and receive horizontally. HV, so you transmit vertically but then receive horizontally. VH, which is the other way around, and VV, meaning that you transmit vertical and receive vertical. Now, by a beautiful theorem called electromagnetic reciprocity, you get that for natural target, VH is equal to HV, up to noise, up to errors. So it means that a SAR image, a polarimetric SAR image, produces 3 images. And those 3 images can be represented in a different way. The lexicographic basis consider HH, HV, and VV. So if you want to show a polarimetric image in lexicographic basis, this would be red, green, blue. Or the widely used Pauli basis. In this case, we have the first channel is HH plus VV. This was red. This was the red channel in the previous picture. The red, no, it was the blue maybe. I think it was the blue, okay, whatsoever. The other guys will tell you. This is HH minus VV and then HV. And so you color code this in your picture. Now, just to make it very, very easy again, you will see polarimetry in details in the next days. But why are people so crazy about using those different combinations? Well, because different ways of the wave to interact with the target result in different combinations of polarization. Just to make it very, very easy, the most simple interaction is called the single bounce. This is what you have from a surface. Just imagine that you are imaging a bare terrain or a desert or the surface of the water, whatever. In this case, we have that the HV signals, so the receiving, transmitting one polarization and receive with the other is very, very low, so you don't even want to take a look at it. HH and VV are strong, they are highly correlated, and they have approximately the same phase, which means that if the sign of one is positive, the other is positive too. Double bounce. Double bounce is something that happens a lot in forest because the wave, just imagine that I am a trunk now, so the wave arrives here, it is reflected by the trunk, it goes down to the ground, it is reflected by the ground back to the radar. And so in forest, this is very important. In this case, again, you have HH and VV, and they have a phase difference of 180 degrees, which basically means that if H is positive, if HH is positive, then VV is negative. So basically, if you form a polarimetric channel as HH minus VV, it means that here you are emphasizing this double bounce. So this HH minus VV would be sensitive to double bounces, and this HH plus VV will be sensitive to surfaces. What is left? Well, if you have the so-called volume scattering, which means that your signal is determined by many different objects like branches with any possible orientation, then you have signal in every polarimetric combination, and you also have signal in HV. And so let's say that the balance between the three components, the HH plus VV, HH minus VV, or HV, is telling you something about what kind of scattering mechanism is dominant for that pixel. Now I stop here with polarimetry. Francesco will show you something. And I think it's now, okay. For example, just to comment here, see that the image here is mostly green. It means that because we have a forest, and so it means that we have scattering from everywhere, so from branches and leaves and so on. It's not very clear with the beamer, but you can see that somewhere in the forest it turns reddish, which means that those are areas where double bounces, so this phenomenon of the interaction with trunks is more important. Anyhow, this is something for the next classes. Because finally, so now let's say that our super basic introduction to SAR is finished. Now we do this quantum leap to SAR tomography. So we pass from 2D to 3D. Again, this is what I said this morning. Why do we link the basics to the most advanced technique? Because they are very similar. So tomography is just an extension of SAR from 2D to 3D. So how does it work? Simply, we fly many times. So we fly many times on parallel orbits. This is exactly what biomass does in its tomographic phase, that is now. Biomass orbits are set in such a way as to illuminate the same areas with 7 consecutive passes every 3 days, and it changes its orbit just a little bit so that you have data from slightly different points of view. In jargon, we say that this is an interferometric baseline, which is a jargon to say the baseline is just this vector in this plane. This plane, if it's not clear, just imagine that I fly many trajectory in this direction. So you fix one particular coordinate, and so it's this plane we are talking about. So in this picture, up here, just imagine that we are flying perpendicularly to the board. So the baseline vector is simply the vector connecting any two orbits, and the normal baseline is simply the projection of this vector onto the perpendicular to the line of sight. What is the trick? You should know it at this point. You should know it. Say that whenever you have an array of antenna, then you can have an angular direction. In our first example, I mimicked having an array of antenna extended over this length to have an angular resolution in this direction. You remember, no? I say, okay, I need to resolve you two guys, and so I need a certain length. Now, if you fly multiple orbits in this way, this is equivalent to having, for each fixed x coordinate, so for each fixed along track coordinate, an array of antennas. In this case, it is an array of satellites. Amazing, eh? It is an array of satellites, or an array of antennas that are 12 meters big, but it's displaced in the other direction. So since the array now is directed like this, it means that I have that I have angular resolution in this plane. So with a single radar and for some bandwidth, I just have a range resolution. So I can resolve you along this line, but I cannot resolve you if you are at the same distance. With the SAR experiment, so just one trajectory, I also have an angular resolution. So now I can resolve you even if you are at different distances. If I fly many times with different trajectory, I also have a further array that is displaced in this direction. So now I also have this angular resolution. What's it for? Well, I said it before, this scene is mostly 2D. So probably for this particular setup, 2D SAR would be enough. But let's say that I want to discriminate you from the beamer. You see, you are more or less at the same angular position, at the same along track position. Well, not exactly the same distance, okay. But if you sit here, you would, okay. Let's say, so imagine at the same distance, so this particular SAR pixel would be the mixture of the guy sitting there and the beamer. If I have an angular resolution in this other direction, then I can resolve them. So again, for this particular scene is not particularly interesting, but for a forest it is, because at this point you can understand which part of the signal comes from the ground, which part of the signal comes from the structure of the vegetation. And this is what tomography is for. So I hope that I managed to pass the concept, because it is easy. It's always nice to do so when you understand something. I think that it's always nice to try to consolidate this knowledge with some calculations, so very simple. We studied that the angular resolution is given by the ratio of the wavelength to twice the aperture. In this case, we have to consider the aperture in this direction, and this is what it is called the baseline aperture. So imagine that for biomass, a third parameter would be, okay, I downloaded the stack of 7 passes. What is the baseline aperture? You ask Klaus. Klaus tells you the baseline aperture. And on this, based on this knowledge, you can calculate your angular resolution in this direction. which means that you can calculate your resolution in the direction of elevation. So with this knowledge, it's bandwidth, synthetic aperture, wavelength, and baseline aperture, you know what is the resolution of your system in 3D. And this is actually what biomass does. So it resolves the signal along different cones within different beams, and then it produces SAR images that are referred to different elevations. So for example, you have that this is the ground within the gray beam, this is this portion in the red beam, and then the red beams, and so on. This is just to recap. This is what tomography does. So it creates voxels and not pixels, meaning that for each voxel, this is a voxel, so it's a pixel for a certain layer. So for each voxel, you have a resolution cell that is no longer the bicycle tire. It is a sort of an egg now, no? And the size of this egg are given by the bandwidth in the range resolution, the synthetic aperture in the along track resolution, and the baseline aperture in the resolution of elevation. So now with this, you can understand exactly what you are looking at. Now, some technicalities, because this afternoon you are supposed to do tomography yourself, starting from a bunch of images. So I just wanted to show you how this is done more practically. So we start from the same expression as we saw before when we commented on interference. So this would be the expression of the complex value of the pixel in the presence of many targets. So we have that whatever is in your resolution cell contributes to that pixel. And we want to generalize this expression for many different orbits. In all those pictures, we always fly in this way. So the first thing that we do, we imagine, so we set for each pixel a reference point in 3D. So before you do tomography, you don't know exactly where the pixel is because you don't have resolution in elevation. So what we do, we take a reference model of the surface topography, and we assume that that pixel is mapped at that position in 3D. This is not correct. It is just a starting point. So this will be our reference position. And then what we want to do is that we want to find a suitable approximation to express the position of the other element with respect to this reference position. So again, this is a simple expansion. You have that the difference between the distance of any point in this resolution cell and the reference position is given by this expression. So where you have the sine and the cosine of the incidence angle. You do this for one orbit, you do this for another orbit, and then you simply take the difference between those two expressions, and you end up with this. Where this is called the double difference. Double because we compute the difference between the reference point in two orbits, and then we compute the difference of those two differences. So when you hear that SAR interferometry or SAR tomography is a double differences thing, this is what we mean. There are just approximations we do. And this double difference physically represents this distance. So it represents the this particular distance that is due to the displacement in elevation, so in this direction, of any point with respect to the reference point. I cannot ask you to understand now. It took me, when I was a student, it took me, I think, a few hours to really put all the pieces together. But what is important here really is that you see that it is nothing else than a series of simple geometrical approximation. If you want to go into it, you have the slides, so it's easy. And at the end, what is important is that we express this double difference in this way, so as a function of the normal baseline between the two satellites and the elevation. What we want to measure is this coordinate, so the position in elevation of some target with respect to the reference point. And this is exactly what we do. So at the end of the day, thanks to those approximations, we have that we can express the SAR pixel in this way. And so we can decompose it in several terms. The first one, this is a common term for all the baselines. So this is a term that doesn't really change if you change the orbit. What changes are the other two terms. So what we can do is that we can do a further approximation and come up with this new equation, which is interesting because the first part, you see, the first term is given by the distances of the reference point in all the orbits. So since we set the reference point and we know the orbit, this is something that you can calculate. So the first thing to do is to calculate and remove this part. And then you have this other sum S. This is only a function of elevation, and this has a special meaning. I said many times today that a SAR pixel is the collection of whatever stays in the bicycle tire, so in the resolution cell. And so this term S of V is just, so you saw that I didn't want to insist too much on the mathematics, but this physical interpretation is important. So this term S of V that pops up from the equations is just a projection of your resolution cell in elevation. This is what you actually need to understand radar tomography. Just imagine again that I have here my bicycle tire, where I have the microphone and the desktop. Imagine that I squeeze it in this direction. So I end up with a single signal that works like this. So like the ground is squashed into this peak and the volume is squashed into this other peak. This signal in elevation is what is actually sensed by SAR tomography. So at the end, what we do is that we express the signal in this way, and exactly by the same reasoning we saw before for the case of the antenna array, we have that different elements. So those two different peaks are mapped to two different spatial frequencies, and those spatial frequencies are are mapped to different elevation position. For the case of the array, we could understand the processing by a simple Fourier transform. This is exactly the same, except that the Fourier transform is done with respect to the orbits. So what we do at the end of the day to do tomography is that, based on this model, first we remove those phases, which we can compute because, again, we know the reference point. After we do that, our mathematical model says that the different images, so just imagine that I take many images and that I take the same pixel out of every image. So if I consider this series of pixels, this is nothing else than the Fourier transform of the projection of my resolution cell. So if I compute a Fourier transform, I can retrieve this signal. And this is exactly how it works. If you remember the expression of the Fourier transform that we saw for time varying signal, for the case of the antenna array, this is exactly the same. It's exactly the same. And what we have is that I can transform a set or a stack, as we say, a stack of SAR images acquired at a different baseline into a set of voxels, where each of those images represents a particular point on this axis. What to say? So I'm nearly finished. Just to say that usually people do not like to reason in terms of elevation. Historically, everyone prefers to reason in terms of height. But this is a bit dangerous because you need to remember that the SAR pixel, the resolution cell of the SAR pixel is not vertical. It is slanted. Remember the bicycle tire. So what you actually do, you are just imagine that you take the bicycle tire, you squash it. What you do with tomography is to recover the squashed signal. This is what you do. So this is what you actually do. This is what you recover. And people usually like to further project this on height in this way. So at the end of the day, this is what visualize, because height is more understandable. You like to think that the tree has a certain height, so you prefer to do tree tomography with respect to height rather than elevation. If you do this, then you can substitute this equation so that the height is linked to elevation v by the sine of the incidence angle. And so you can express your data in this way. This is important for me to say because all the other teachers will use this formalism. So you need to know it. Where we can say that a single SAR pixel is obtained by summing the squashed signal, so the projection of your resolution cell in elevation, according to this factor that are called the interferometric wave numbers or the phase to height conversion factor. This is the formula. Those are numbers that come with the data, meaning that when you download biomass data, they are calculated for you. And on this basis, you have all it takes to do tomography. I know it's a bit late, but I'm nearly finished. There is an aspect that you need to consider. This is called in jargon terrain flattening. What does it mean? We say that our approximation was based here on the choice of a reference surface. I say that, okay, I need to choose a reference point for each pixel. This means that when I do my tomography, my forest will appear with respect to this reference point. So if, for example, let's say this is, so the yellow terrain here is the true terrain, and the red curve is my reference elevation that I take from somewhere else, that I can just guess. Then it means that when I do tomography, also the terrain will not appear at 0 meters. It will appear at this position. So the forest will appear in a position that is relative to the reference point. Of course, if you know the actual topography, then you can use it. And in this case, the terrain will appear at 0. And so indeed, for biomass, an important topic is to be able to estimate terrain topography so that when we do tomography, we know that the terrain appears at 0 meters. And this is the way we can provide a physical interpretation of what we see in terms of biophysical parameters. I think this is really it. Just to say that this is a simple way to do tomography, but believe me, this is the right way to understand tomography. So stick to it. Truth is that people, and you will see this later on this afternoon and tomorrow morning, people like to formulate tomography in a different way, passing through interferometry, coherence, blah, blah, blah. Why is that? Because basically in this way you are able to use more powerful mathematical methods. And by more powerful, I mean methods that can give you a better vertical resolution. So you can improve your vertical resolution so you have a better discrimination between trees and the canopy and so on. And also in general a better imaging quality. Now I didn't comment too much on like the side lobes or different effects, but let's say that those methods can help you produce sharper images. But of course, this is not for me to say because I'm done, and you will enjoy this part with the other lecturers. And this is it. I'm nearly on time. Come on. Thank you.